Alrighty, welcome back to 353. So today, get to talk about more locking. Yay! So, there are these things called monitors built into some languages. Who here has used Java? Alright, so have you done threads in Java? No. Could you do threads in Java? No? So, you can. So, in some languages, there are these things called monitors. You know, when they made object-oriented programming, where literally everything is an object, developers wanted something easier to use than like a mutex. So, what you can do is mark a method as monitored, and then let the compiler handle locking for you. But of course, if you don't know how a mutex actually works, and it actually uses a mutex under the hood, and it's really easy to screw them up, well, they might get screwed up. So the rules for monitored methods is basically what the compiler will do is create one mutex per object, and then in every method you marked as monitored, it will do a lock call at the beginning and then an unlock call at the end, so you have mutual exclusion between methods for the same object. So in Java, if you have the unfortunate task of having to write Java, well, there's a synchronized keyword, and that is basically an example of a monitor. It's just what Java calls it. So say I wanted to create a class called an account, and I had an integer balance, so I was trying to run a bank. We'll get to run a bank and screw it up on next Tuesday. But for now, assume I'm trying to run a bank. I create a class that represents an account. I give it an int that's supposed to represent the balance of the account. And then, well, if I have multiple threads and I write a method just called deposit that adds money to the account, and a method called withdrawal that subtracts money from the account, I could have data races if I have multiple threads here, right? Multiple threads could be calling deposit, withdrawal. We don't want to have some inconsistent result. So what I might do is I might just put a synchronized here, and what that will do is the compiler will transform the code for us. So it would basically create a mutex in this class called monitor, and it would transform the method calls to, in deposit, it would like lock this stop monitor, and then do the actual adding to the balance, and then it would unlock it at the end. And for the withdrawal, it would go ahead, add it at the beginning, and unlock at the end. So that way, I wouldn't get into data races, hopefully, theoretically, with this. But we'll see later at the end of the lecture when we talk about deadlocks. Your code can have issues with this still. So there's also another synchronization thing we can use called condition variables. They're very badly named. They behave kind of like semaphores. Basically, they allow you to create your own custom queue of threads. So I like thinking of them just as a queue. And the name condition variables is because, well, they're supposed to predict a variable until it reaches a certain condition. If it was semaphores, the condition would be, oh, well, the value has to be greater than 0 in order for it to be able to subtract for it. But if you don't want just that condition, you can use condition variables to accomplish that for us. So their type is pthread_cond_t, and while they're just called a condition variable, they have an initialization function that has some attributes that we can ignore. They have a destroy, and annoyingly, they have a method called signal. Has nothing to do with actual signals that get sent to processes. It just has to do with what happens to that queue. So what signal will do, this condition variable, I like thinking of it as just a queue of threads, or like a waiting queue. So what that will do, signal will just wake up the first thread in line and unblock it so it can go ahead and run again. There is a function called broadcast that we can ignore, but it will essentially unblock every thread that is currently asleep in the queue. And then similarly to semaphores, there is a wait, and you might see here that it is paired with a mutex. So how that works is it will atomically add itself to the queue, and also the rule is you can only call wait while that thread has this mutex locked, and it will add itself to the queue, and then before it gets blocked, it will go ahead and also unlock the mutex so that another thread can hopefully change the condition variable that it's waiting on, which we'll see examples of. It could be anything we want, and make sure we don't have any data races with it. Then there's also a timed wait, just in case you get into that situation where you might, block forever. You could just put a timeout so that after a certain amount of time, you will get unblocked. So for the purposes of what we need to know, aside from creating it and destroying it, we'll just argue about wake, that add wait, which just adds the thread to the queue, and then signal that wakes up a thread. Again, don't have to worry about broadcast, but that would wake up all threads. So, like I said, has to be paired with a mutex. So any calls to wait must already hold that mutex. Calls to signal or broadcast, you don't have to have the mutex acquired when you call them, doesn't really matter. And why? Well, we need to prevent data races. So thinking of that condition variable as a queue, well, it needs to safely add itself to the queue, and it also needs it as an argument because before it gets unblocked, it will go ahead and unlock it before it blocks and goes to sleep. And the other rule is whenever that thread gets unblocked, it will only return from wait when it has reacquired the mutex. So the mutex will be locked when you call it, and then locked when you return from it. So you don't have to worry about any weird locking conditions. So we can have one mutex that protects multiple condition variables, and like I said, we will only consider calls to wait and signal. So to understand again what wait does, so it doesn't contain any data races, and it basically does three things whenever you call wait. The current thread that is executing will add itself to the queue for that condition variable. It will also unlock the mutex, and it will also block, so it will also go to sleep. It now can no longer run. So when eventually a thread that is in the queue gets signaled, gets unblocked through a signal or a broadcast, then if it actually gets scheduled to run, because again, remember, we're up to the scheduler, so we don't know when it will actually execute it. What it will do is it gets unblocked, so it can run. Again, we don't know when it can run. And then it will try and lock the mutex again, and wait will finally return when it gets the mutex. So that is basically how wait works. And if we wanted to, we could rewrite that producer-consumer example from last lecture using condition variables if I want. You may or may not think this is easier than center-fors, but basically, my condition variable, I can just keep track of the number of filled slots, and then I can have a queue that is waiting for a filled slot, or a queue that is waiting for an empty slot. And then, well, I would be reusing this mutex, so this mutex would be protecting any data races to the number of filled slots variable, and I can just go ahead, check the value, and make sure that it is actually valid. So in the producer, my condition is basically I only want to go to sleep when the number of filled slots is equal to the buffer size, or capital N. So that could be my condition. So while everything is full, I just want to put this thread to sleep. I want to wait. So I'm putting myself in this has empty queue. So I'm saying, okay, I'm waiting until there is an empty slot, and then I give it the address of the mutex so it can go ahead and unlock it, and hopefully another consumer thread can actually execute. If it gets woken up, it would reacquire the mutex, and if the number of filled slots does not equal to n, so it's not full, it will go ahead and just fill a slot, increment the number of filled slots because we just filled a slot, still has the mutex, so we don't have any data races, and then it could go ahead, signal any thread that's waiting for a filled slot, and then unlock the mutex. And then similarly for the consumer, well, we need to put it to sleep when the number of filled slots is 0, so there's no data for it to get. and then it can put itself in this has filled queue, and then, well, eventually when it gets to run, it would reduce the number of filled slots, and then it could signal any producer threads that are waiting for an empty slot, and then unlock the mutex. So, this easier or harder to read than the center-for example? Easier, right? Makes a bit more sense. So, I had some people argue that the center-for was easier for this. That one, I don't know, a bit more borderline. I would argue that this is easier to actually read, but whatever floats your boat, I guess. Yeah?
Can you explain how does unlock happen in the wait?
So how the wait works, so say that, I don't know, everything's filled here, right? So we have all filled slots. So this producer thread needs to go to sleep because it's waiting for at least one empty slot, right? So it would put itself into a queue of threads that are waiting for empty slots, and then it would also unlock the mutex and then actually go to sleep. So I would have like just one thread in this has empty queue, and because it unlocked the mutex, well, what could happen is a consumer thread could run, right? Yeah.
So when you said go to sleep, it just means that like nothing after the for loop gets done, right?
Yeah, so it'd get blocked, goes to sleep, can't execute anymore. Yeah, it's just in the middle of the wait call. Okay, so we can have a smaller example where we can see if we have screwed up using one. So let's take this example, and I will give you a second with it. Whoops. So the idea, again, with the condition variables is you are waiting for something to be true. It doesn't have to like literally be a Boolean value true. In this case, it is. I will just assume that I have a global variable called condition. And then initially it is false. So the way I want to use my condition variable is, okay, well, I will lock the mutex, make sure there's no data races with it, check. So while the condition is false, I will go to sleep because my intent is that I only run this line of code, only run when, so I only want to run this line of code if the condition is true. So, assuming I have two threads, thread 1 and thread 2, thread 1 would start executing here, thread 2 would start executing here. Is there any issues with the following code, or AKA, is there any possibility that I can either run when that condition is false, or I can go ahead and also maybe, I don't know, maybe a thread just goes to sleep forever. Now, give you a hint, it's more likely that there is a possibility where a thread can go to sleep forever. So T1 is stuck in the while loop. So let's assume T1 goes first, so it would acquire the mutex. So here, I'll even put up here, mutex, and then which thread has it. So mutex is currently held by thread 1. And then I could also write my condition variable called condition, and then that could just be a queue of threads I'm keeping track of. Initially, it would be empty. So if thread 1 executes first, it could acquire the mutex and then check the condition. So while not condition, well, currently it's false, so not condition is true. So it would go into the body of the while loop and then it would hit this wait. So when it hits this wait, it essentially would atomically add itself to the queue, and then give up the mutex. So it would look like that, and then thread 1 can't run anymore, right? So thread 1's put to sleep, it is on that queue. Now, if thread 2 runs, okay, well, it changes that condition equal to true. So this gets updated to true. And then it would signal, so it would wake up thread 1. And now thread 1 could execute again. In this case, thread 2 is done. So if we choose thread 1 to execute again, well, as part of returning from this wait, it will try and reacquire that mutex. In this case, no other thread holds it. So it could grab the mutex. Then it would go check the condition again. The condition is not true, so it's false. So we break out of the while loop, and then this line of code runs while the condition is true. No problem there, that's what we wanted. And then we unlock the mutex. So we go back to this, and everything worked, no problem. Yeah.
I thought the second time you did the while not condition, the condition is empty, so shouldn't it execute in the while loop?
So condition is this Boolean.
Oh,
Cond is the name of the queue.
okay.
Yeah, oops. Okay, so here, let's rewind so we can bring all the threads back. So initially the condition is equal to false. All right. Any other is there a sequence of concurrent switching between thread 1 and thread 2 that causes something bad to happen? Yeah. Yep. Yep.
Thread 2 doesn't lock, so after it runs condition, it should just give up.
So what you're saying, so one thread has to execute first. You're saying thread 2 executes first? So what happens if thread 2 executes first? Well, then it changes the condition from false to true. Whoops, that is the wrong tool. So it changes the condition from false to true, and then it would signal nothing to wake up, so it doesn't do anything. Then thread 1 executes, acquires the mutex, checks the condition, it's true, so it jumps right here, and it running this line of code while the condition's true, all good, unlocks the mutex. Nothing bad happened there, right? All right. Anything else that could possibly go bad? There's another one on Discord that's that's close. I think you might have got bailed out by Discord. So what could happen that's bad is thread 1 executes first. So thread 1 executes first, goes ahead, acquires the mutex. It check the condition, so the condition's currently false. So the next line of code it would run is putting itself on the queue, but I can context switch over to thread 2 right now. So at this exact point, I context over to thread 2. Thread 2 just changes the condition to true. And then it would signal, and then nothing to wake up, so it's all good. Then we switch back to thread 1. Thread 1, okay, well, it would hit this wait. It would atomically put itself in the queue. and also give up the mutex. But now, thread 2 is never going to wake it up again, right? So this is another example of lost wake up, where that thread goes to sleep and never wakes up. Everyone agree with that? That's bad? All right, fix it. Yeah. Yeah. Yeah, so my problem was, well, I had a mutex that was protecting a read to condition variable, but I have a data race because there's also a write that is not protected by a mutex. So with that same mutex, I should probably lock it here, and then I can unlock it right after I update it, or I could unlock it after I signal. Turns out it doesn't matter. Where do you want to put the unlock, before or after? After? Sure, let's put it after. So now, if I just have that lock and unlock call, what happens if we get the same unfortunate sequence of threads again? So I'll move it back up. Oops. So initially there are no threads in that con queue, no thread has the mutex, and the condition is equal to false. So now what happened before is thread 1 executed first. It would go ahead, acquire the mutex. So now it has the mutex. Then it would check the condition. Okay, so that's like a memory read of the condition. It's false, so that's not true. So it would go into the body of the loop. And then at this point, right before it executed the con wait is where we had the issue before. So now what happens if we context switch over to thread 2? So if we context switch over to thread 2, the first thing it's going to call is this lock of the mutex, and can it make it by that? No, right? Only one thread can have a mutex at a time, so it would get blocked, it couldn't execute. We have no other choice in this case but to context switch back over to thread 1 to make some progress. And then what thread 1 would do, would call wait. So it would go ahead, add itself to the queue, and also unlock the mutex. And now it's asleep, it can't execute anymore. The only thread we could execute is thread 2. So it would hit the lock call, and it would acquire the mutex, go ahead, update the variable from false to true. And then it would signal it, so it would wake it up. So now we have woken up thread 1. But thread 1 can't make any progress, right? Because it would reacquire that mutex. And currently, thread 2 has the mutex. So it's not going to return from wait until thread 2 actually unlocks the mutex. So next thing thread 2 would do is thankfully unlock the mutex. So it would look like this. Now, if we chose, the scheduler chose to execute thread 1 again, okay, well, it would try and reacquire the mutex. So it turns out nothing's holding it. So it would acquire the mutex, and now it is done with this wait function. Then it would go back up, check the condition. Oh, okay, well, the condition was true. Okay, well, great. Now I just execute this line. That line's running while the condition is true. So some of you might feel clever of like, why the hell did you write this while? Why didn't you just write if? Does anyone have that feeling? All right, so we have one person with that feeling. Anyone want to tell them why they're wrong? So I will give you, in this case, it could actually be an if. That is fine. But what about if I had 3 threads. So I have 3 threads, same idea. In thread 1, I want condition should be true. And initially, I will have condition equal to false. So I have that same thread, but I just changed the while to an if. And then in thread 2, it's the corrected version. So this will go ahead, update the condition variable equal to true. And then I also have thread 3, which just sets it to false. And it doesn't have a signal here because, well, if it sets it to false, the condition is waiting for until that value is to true, so it wouldn't have changed it to true. So now, looks like everything's locked properly, so I have no issues with the condition variable. So if I just change that while to an if, is there any possible interleaving of thread 1, 2, and 3? That could happen such that, this line executes while the condition is false. Yeah?
We can context switch from thread 2 to 3 after the unlock and before the signal.
Okay, so let me just write out a few variables here. So you said we can context switch to thread 3?
From 2 to 3 after it unlocks, but before it signals.
Before it unlocks, but before it signals.
Like after the mutex unlock in thread 2, but before the signal in thread 2.
Okay, so the suggestion is thread 2 executes first. So it acquires the mutex and then updates the condition equal to true. Then unlocks. So now thread 3 could run, right?
I mean, like thread 1 has to execute first, go into the wait, and then we switch to thread 2.
So thread 1 actually has to run first. So let's rewind it all the way to the beginning. So, bad thing that could happen, thread 1 executes first. So it acquires the mutex. That is A-OK, no one has the mutex. Now, looking at the other threads, they both do a call to lock of the mutex, so there's nothing else that could possibly run aside from thread 1. So here, check the condition. It's false, so it would hit this wait. As part of the wait, adds itself to the queue. Oops. And then also unlocks the mutex. So now either thread 2 or thread 3 could run. So you're saying thread 2 runs first, right? So thread 2 runs, it acquires the mutex, updates the condition to be true. Then it unlocks the mutex. And now before it hits the signal, we context switch over to thread 3. Thread 3 acquires the mutex no problem. Changes the condition from true to false. And then unlocks the mutex. Oops. Now, at this point in time, only thread 2 can execute next because thread 1's blocked. So next thing it's going to do is signal, which is just going to wake up thread 1, and it is going to try and reacquire that lock to return from wait. Turns out thread 2 can't do anything. Thread 1 is the only one that can do anything. So it would acquire the mutex. And then executes this line of code, and the condition is false. Crap. Whew, everyone good with that? So how would I fix that? The fix, make this a while. So, there are cases like the previous one. Oh, yeah?
Did you swap unlock and signal?
Yeah, okay. So yeah, what about if I just give these two the old swapperino? Does that work? All right, so let's try with that, swapping them and seeing what happens. So the situation I was in where the bad was about to happen is, well, that's basically the first thing. So I'll rewind everything. So let's rewind most of it. Thread 1 is just going to be sitting here in the queue. And no one has the mutex. Am I okay if I make that leap, rewind everything, thread 1's just in the queue? Okay, so let's see what could happen now. So thread 2 runs next. It acquires the mutex. It updates that condition to be true. And now it has no choice but to signal. So it would signal, and then we unblock thread 2, or thread 1, sorry. So thread 1 can run. Can it run right now? No, because it would try and reacquire that mutex, and thread 2 currently has it, so couldn't execute. But you know, the only thing that could happen is thread 2 finally calls the unlock that we switched. So now no thread has the mutex. So right now, either thread 1 or thread 2, thread 3 could execute, right? Yeah?
Wait, this is because in the wait call in thread 1, it grabs the mutex?
Yeah. Yeah, so in this case, so I might be okay if I make that switch if it happens that thread 1 executes next, gets that mutex back, and then now it's true. So now we're good. But we don't know if thread 1 or thread 3 is going to actually execute next. So it might be the case, and very likely this would probably work due to how the scheduler works, but still technically has the issue, and then these are one of the 7-year bugs that you will never ever fix. So in this case, I don't have to pick thread 1 to execute next. It could be thread 3, which goes through and does the whole problem again where it switches it to false. Thread 1 requires the mutex and then runs that line while it's false. Oh, okay. So any questions about that? Yeah?
Would we have that same problem if we just got rid of thread 2 and added the signal to thread 3?
So if we got rid of thread 2,
Yeah.
so if we got rid of thread 2, then it's not possible to actually execute this line because no thread is ever going to change it to true, right? And we only want this line to run while the condition's true.
Oh, but if, let's say the condition started out as true,
Yeah, so if the condition started off as true, then I could, yeah, but if the condition started off as true and then all the threads only switch it to false, I don't know what order they're going to be scheduled in, so it's likely that that one thread is never going to be able to run, or there's a situation where it might never run. So with them, typically you want to make sure that you eventually change that condition to be true, otherwise it'll sit there forever. And yeah, and other things, like if I add a signal to here, even though I don't change the condition equal to false, not going to change the behavior, it's just going to be inefficient, so I just wake up a thread that would just wake up, reacquire the lock, read the condition again. If it's actually in a while, it just reads a false again, and then goes back to sleep, and then it's kind of just a waste of time, but it doesn't actually affect my correctness if I put a signal here or if I put in however many signals I want. If I just want to just throw some signals around for fun, I am able to, but like everything, it'll just make your program go slower, and it will just make things harder to read. All right. Whew, all good with that? All right, so other fun things. So we got that, we got that. So yeah, like I said, so they do serve a similar condition to center-fors. You can, like, center-fors are basically a special case of condition variables where it's just protecting a value, like it's just protecting an integer, and it'll essentially call wait when the value is 0, and then whenever a thread posts, it would just signal. So it would wake up a thread, and then it would only decrement if the current value is 0. Turns out, if you're like a computer science nerd that likes theory, you can always implement one in terms of the other. However, the question of whether or not you can actually read your code after that is very questionable. So in general, if you have like a complex condition that's more complicated than just an integer, use condition variables. It's going to be a lot easier to read. So we'll have an example in the next one, but once you actually like care about performance and not just correctness, you have to consider like locking granularity. So that's the extent of your locks or how big that critical section is, because, well, you need locks to prevent data races, but if you have a big chunk of code and it's protected by a lock, only one thread can execute at a time, then suddenly your program is slow, and if it's really big, you shouldn't have used the lock anyways. Just run with just a single core, and it'll probably be faster. So for like an example, if I want to parallelize a hash table, which you will do, well, should I just lock the whole table and then I don't have any data races? Well, it might be slow. Should I do something else? Should I only lock like individual elements? Should I think about something better to do? Might be something to consider if we actually care about performance. So things to consider in real programs whenever you try to make your program not have data races. There's going to be some overhead of using locks. So if like the operation you're trying to protect is really small, like what we saw with just incrementing a integer, well, it might be faster, like take some time to do the locks, has a queue, takes some time to do the unlock. So that overhead might be more than you actually care about than just running it on a single thread. Might also have contention, so you might also have like a lot of threads all fighting over the same lock, in which case, well, they're going to be asleep a lot of the time, and you're not going to have any parallelism. And then the third one, which we haven't got into yet, which is the funnest subject, is deadlocks. So, and like I said, with overheads, you have to also allocate some memory for a mutex. So if you have billions of them, even if they're only 1 byte, it's going to take up a lot of space. Takes some time to initialize them, and destroy them. Takes time to lock, takes time to unlock, and the more locks you have, the worse it's going to be. But the most important thing, and the thing that will definitely come up on an exam, and you will definitely hit probably in your actual programs, as soon as you have more than one mutex, you might have the chance of having a deadlock. So a deadlock is basically you'll get into a situation where a thread can no longer make progress anymore. At least one thread, sometime all threads, and then your program looks like it just grinds to a halt. But you could consider just like a single thread deadlocks if it can't make any progress anymore. So there are some conditions you need to have for a deadlock. So the first is mutual exclusion, which we're just going to argue about deadlocks for mutexes. So of course we have mutual exclusion. Second condition is hold and wait. So you have to have acquired a lock and you are waiting for a different lock. The third is no preemption, so you just can't randomly take locks away from threads. And then the fourth is a circular wait. So you're waiting for a lock held by another process or another thread. So these all have to be true in order to have a deadlock. And it turns out we can break either the second condition or the fourth condition fairly easily and prevent deadlocks. But first, just to illustrate the example, this is an example of a deadlock. So we have two processors, could be threads. If we're sharing the lock between processes, could be processes. But say we have two threads. The code that we write in one is to acquire lock 1, get lock 2, and then we release lock 1 and release lock 2 and then lock 1. And the other thread, we lock 2, then lock 1, and then release lock 1, release lock 2. So, whoops, typo. So, could get in the situation where we have thread 1 executes first, it locks lock 1, and then we context switch over to thread 2. It locks lock 2, and now neither thread can make any progress. So thread 1 has lock 1, thread 2 has lock 2, and if we chose thread 2 to execute, well, it's waiting for lock 1, which is held by thread 1. If we chose thread 1 to execute, it wants to get lock 2, that's held by thread 2. Neither can make any progress, and we are now screwed. So, that clear with everyone? All right, so in order to actually prevent them, so to prevent a deadlock, I can either ensure order. So if I always acquire locks in the same order, I don't have that circular wait problem. So say lock 1 and lock 2 were like global variables or something like that, so their addresses didn't change. Well, if I just have acquire lock 1 and then acquire lock 2 in that order, doesn't matter, I won't get into any bad situations. So if I have two threads running this, well, thread 1 could go ahead and acquire lock 1, and then if we switch to thread 2, well, the first thing it's going to do is try and acquire lock 1. Not going to be able to get it, so it's going to have to wait until thread 1 goes back, executes, acquires lock 2, and we can go ahead, run our protected code, and then we're all good. So this code will not deadlock because, well, one way to think about it is that you only get lock 2 if you already have lock 1. So the other way to do it is using that try lock that we haven't used before. So the second condition is like hold and wait. So if I don't know, like if I can't ensure a absolute order of locks, well, this is another thing I can try. So I could lock the first lock. So I have lock 1 now, and then I can do a try lock of lock 2. And then this will tell me whether or not I got the lock or not. So it will return 0 if I successfully got the lock. Otherwise, it will return some value that is not 0. If I did not get the lock, well then I can make the assumption that another thread has acquired lock 1 before me. And it might be waiting on, like another thread has lock 2. So it might be waiting on lock 1 as well. So what I'll do is I will just unlock lock 1. So I just give it up. So I had lock 1, and then I try to get lock 2. If I don't get it, I give up lock 1. And then I can wait for a bit. I can yield. I can do whatever I want here. And then after a bit of time, I can try and reacquire lock 1 again, and then try to get lock 2 again. If eventually I actually do acquire both locks, then I can run this code knowing I have both locks acquired. And then I can go ahead and unlock them both while I am done. So, questions about that? Yay, now we saw a situation we can use try lock for. So, now we can wrap up if we don't have any other questions. So now, we explored some more advanced locking. We'll have a larger example on Tuesday, so do not forget that one because it will look somewhat like the lab and code you will actually write in your life. So what we did today, we have now another tool to ensure some type of order. So that would be condition variables. There are going to be a bunch a lot clearer for like more complex condition signaling. They're basically just a queue. And then in terms of real world performance, the locking granularity, so how much code you have between lock and unlock, is going to affect the performance of your program. So you might want to have more locks that cover smaller pieces of code than just one lock that covers everything. So if we've used Python and thought it was really, really slow when you're using threads with Python, it's basically because they use one gigantic lock to lock all of Python because they didn't want to argue about every single thing and like make thousands of locks. Although recently they've changed it where Python actually works with threads much better than it did before. But if we have multiple locks, then we might have deadlocking situations and you have to prevent them. So with that, just remember, pulling for you, we're all in this together.